Hashing is very important in cryptography, and we will soon see why. The basic idea of a cryptographic hashing function is that any data, no matter what the size or the type, can be converted into a fixed size text representation. The source data can be text data or it could be binary data, it doesn't matter. The fixed size representation is called a hash or a digest. But the hashing function has some incredibly useful properties. For one, the hash or the digest is unique to that data. There are no collisions. Two different pieces of data cannot hash to the same value. But that same piece of data will hash to that same value every time when we apply that hashing function. Secondly, data cannot be recovered from the hash. In other words, if someone gets hold of the hash, they cannot recover the original data. So on the screen, you see some XML data. If you apply a hashing algorithm to it, you get the hash, a fixed size hash. But you cannot go from the hash to the data. There are several algorithms that are popular which can create a hash. Most popular of them are SHA-2 family of hashing functions, the SHA-256, the SHA-512, etc. all fall under that. SHA-1 is no longer used. The size of the hash depends on the algorithm used. SHA-256 will create a 256-bit output hash. SHA-512 will create a 512-bit output hash, and so on. But what's the whole point? Why do we need to do this? It turns out that a hash is extremely useful in cryptography. Let's take a few examples. Let's take the example of a password. Passwords are usually stored as a hash in the identity management system and not as an encrypted password. Usually what's done is that some random data is added to the user's password and then a hash is created. The hash and the random data, also called as the salt, are stored in the database along with the user's other identity information. At the time of the authentication, the user's entered password goes through the same algorithm and then compared against the stored hash. If they match, then the authentication is successful. Now this works nicely because two different passwords cannot hash to the same hash value. Also, you cannot recover the password from the hash. Both of these points are extremely important. Here's another example of the importance of hashing. The example shows a Java 17 download page from Oracle's website. Notice the SHA-256 link. The hash value at the bottom is what you get if you download the first one, and then compute the SHA-256 hash for that compressed tar file. This is a very popular way of figuring out if the entire file has been downloaded correctly, or to make sure that nobody has tampered with the contents. In authentication systems, hashes are used frequently to figure out if a message has been tampered with. So for example, if application A sent a very important message to application B, if B wants to figure out that nothing has happened to the message along the way, then it can definitely use the hash to do so. Once again, I should mention that creating a hash is not an encryption.